Hello, and welcome to another mind-blowing episode of Spaceverse. Today we are going to explore a radical idea that challenges everything we think we know about the origin of our universe. What if the Big Bang was wrong? What if we live inside a black hole? And what if there are countless other universes inside other black holes? Sounds crazy, right? Well, not according to some physicists who have proposed this theory as a possible explanation for the mysteries of the cosmos. In this video, we will examine their arguments, look at some evidence, and see if we can make sense of this bizarre notion. So buckle up and get ready for a wild ride into the unknown. This is Spaceverse. We live inside a black hole. The conventional view of the Big Bang is that it was the beginning of everything. About 13.8 billion years ago, all the matter and energy in the universe was compressed into a tiny point of infinite density and temperature called a singularity. Then, for some unknown reason, this singularity exploded and started to expand rapidly, creating space and time along the way. This expansion is still going on today, and it explains why the universe is so big and diverse. But there are some problems with this view. For one thing, we don't know what caused the singularity to explode in the first place. Maybe it was bored. Maybe it had a bad day. Maybe it sneezed. We don't know. For another thing, we don't know what happened before the Big Bang. According to Einstein's theory of general relativity, which describes how gravity works on large scales, time and space did not exist before the Big Bang. But this theory breaks down at very small scales, where quantum mechanics takes over. Quantum mechanics describes how matter and energy behave on subatomic levels, and it suggests that nothing can be infinitely small or dense. So there must have been something before the singularity, but we don't know what it was or how it worked. Maybe it was a party. Maybe it was a fight. Maybe it was a game of tic-tac-toe. We don't know. This is where some unconventional scientists come in. They suggest that there is a way to avoid these problems by replacing the singularity with something else. A black hole. A black hole is an object so massive and dense that nothing can escape its gravity, not even light. It forms when a very large star collapses under its own weight at the end of its life cycle. The boundary between the inside and outside of a black hole is called the event horizon. Anything that crosses the event horizon is doomed to fall into the black hole and never come out. But what if there is something else inside a black hole? What if there is a whole new universe? This is the idea proposed by Nikodem Poplawski of the University of New Haven. He argues that our universe was born inside a black hole, and that each black hole may contain a new universe inside it. He calls this theory cosmological natural selection, because it implies that universes can reproduce and evolve through black holes. According to Poplawski, when a star collapses into a black hole, it creates a seed of a new universe inside it. This seed is very small and dense, but not infinite. It has a finite size and mass, determined by the mass of the original star. It also has a lot of spin, because some black holes spin very fast. This spin creates a huge amount of torsion, which prevents the seed from collapsing further. Instead, the seed bounces back and starts to expand rapidly, creating space and time along the way. This expansion is similar to the Big Bang, but it happens inside a black hole instead of from nothing. The new universe inherits some properties from its parent universe, such as the laws of physics and the constants of nature. But it also has some variations, such as different initial conditions and parameters. This means that there could be many different universes inside different black holes, each with its own characteristics and history. Some of them may be similar to ours, while others may be very different. Some of them may be hospitable to life, while others may be hostile or barren. Poplawski's theory also implies that our universe is inside a black hole as well. This black hole belongs to another universe, which he calls our mother universe. The mother universe may have its own mother universe, and so on. This creates a hierarchy of nested universes, each one inside a black hole of another one. But how can we test this theory? How can we find out if we live inside a black hole? One way is to look for evidence of Hawking radiation. Hawking radiation is a phenomenon predicted by Stephen Hawking in 1974. He showed that due to quantum effects near the event horizon, black holes are not completely black. They emit some radiation that reduces their mass over time. Eventually, they may evaporate completely. If our universe is inside a black hole, then it should also emit Hawking radiation to its mother universe. This radiation would appear as cosmic microwave background, CMB, to us. Cosmic microwave background is the leftover radiation from the early stages of our universe's expansion. It fills the whole sky with a uniform temperature of about 2.7 Kelvin. However, Poplawski predicts that Hawking radiation would create some anomalies in cosmic microwave background. It would make it slightly warmer in some regions and cooler in others. It would also create some circular patterns called rings in cosmic microwave background maps. These anomalies have not been detected yet by our current instruments, such as Planck satellite or WMAP satellite, but they may be found by future missions or experiments. Another way to test Poplawski's theory is to look for gravitational waves. Gravitational waves are ripples in spacetime caused by violent events, such as collisions or mergers of massive objects like black holes or neutron stars. If our universe is inside a black hole, then it should also produce gravitational waves that escape to its mother universe. These waves would appear as background noise to us. However, Poplawski predicts that these waves would have some distinctive features that distinguish them from other sources of noise. They would have a specific frequency spectrum and polarization pattern. These features have not been detected yet by our current detectors such as LIGO or VIRCHO, but they may be found by future observatories such as LISA or BBO. So far, Poplawski's theory remains highly speculative and controversial. It has not been proven or widely accepted by the scientific community. It faces many challenges and criticisms from other physicists who doubt its validity or consistency. How does Poplawski's theory explain inflation? Inflation is an extremely rapid expansion of spacetime that occurred shortly after the Big Bang. It explains why our universe is flat, smooth, homogeneous, isotropic, and has tiny fluctuations in density and temperature. Inflation also solves some puzzles such as why our universe has more matter than antimatter, why there are no magnetic monopoles, and why there are no observable relics from before inflation. According to Poplawski's theory, inflation could be driven by torsion, which acts like an effective negative pressure that pushes spacetime apart. Torsion could also generate primordial gravitational waves that could be detected by future experiments. How does Poplawski's theory explain dark matter and dark energy? Dark matter is an invisible form of matter that makes up about 27% of the total mass energy content of our universe. Dark matter interacts only through gravity, but its presence can be inferred from its effects on visible matter, such as galaxies, clusters, and gravitational lensing. Dark energy is an unknown form of energy that makes up about 68% of the total mass energy content of our universe. Dark energy causes an accelerated expansion of spacetime, which counteracts gravity. According to Poplawski's theory, dark matter could be explained by torsion particles, which are massive spin 1/2 particles that interact only through torsion. Dark energy could be explained by torsion fields, which act like an effective cosmological constant that drives inflation. How does Poplawski's theory relate to string theory? String theory is an attempt to unify all fundamental forces and particles into one framework based on vibrating strings or membranes in higher dimensions. String theory predicts extra dimensions beyond our familiar 4 dimensions, 3 spatial plus 1 temporal, which could be compactified or curled up at very small scales. According to Poplawski's theory, extra dimensions could arise naturally from torsion geometry, which allows for more degrees of freedom than standard Riemannian geometry used in general relativity. Torsion geometry could also accommodate string-like objects or branes as solutions to torsion equations. Here are some of the recent methods that discloses the expansion of black hole and more. A new method was developed to measure the distances of galaxies and supermassive black holes at cosmic noon, using images at different wavelengths and a statistical approach. This method overcomes the previous limitations of spectroscopic distance measurements for individual galaxies and allows for a more accurate determination of galaxy collisions and mergers. Another new discovery was made using Hubble Space Telescope data, revealing a rapidly growing black hole in the early universe that is considered a crucial missing link between young star-forming galaxies and the first supermassive black holes. This black hole, nicknamed GN7, is located in a galaxy that is forming stars at a rate 1,000 times that of our own Milky Way. The black hole is producing ultraviolet and infrared light that is consistent with the radiation expected from materials that are falling onto it. This discovery provides new clues on how supermassive black holes grow and evolve through cosmic time. Another study suggested that Hawking radiation inside a charged black hole could be enhanced by quantum interference effects, leading to a faster evaporation rate and a higher temperature than expected from classical calculations. This could have implications for the information loss paradox and the quantum nature of gravity. A new review article discussed the status of cosmological natural selection, a hypothesis that proposes that universes can reproduce and evolve through black holes. The article summarized the motivation, successes, and challenges of this hypothesis, as well as its relation to other theories, such as string theory and inflation. A new discovery was made using ALMA data, revealing a rapidly growing black hole in one of the most extreme galaxies known in the very early universe, named COS 87259. This black hole is considered to be a new type of primordial black hole, heavily enshrouded by cosmic dust and emitting most of its light in the mid-infrared range. This black hole is also generating a strong jet of material moving at near light speed through the host galaxy. The discovery of COS 87259 and its black hole sheds light on the abundance of very early supermassive black holes and their formation mechanisms. Thank you for watching this episode of Spaceverse. If you enjoyed this video, please like, share, comment, and subscribe. And don't forget to hit the bell icon for notifications on our next videos. Until then, stay curious and keep exploring. And remember, don't go near any black holes unless you want to end up in another universe. Or maybe you already did. Who knows?